Morning, dear students. Today we are going to learn a new section in the mitochondria chapter, that is oxidative phosphorylation. Look to that term, oxidative phosphorylation. While noticing that term itself, we can understand to certain extent what is that process. Look, first part oxidative, and the second part is phosphorylation. So two reactions are happening, oxidation and phosphorylation. And because of these two reaction, what is forming ATP? So that is oxidative phosphorylation. So simply, I'm going to explain once more. It is a process of synthesis of ATP from ADP through a series of oxidative reactions. And these reactions are happening inside the mitochondria. So that is simply oxidative phosphorylation. See its definition. It is a process of synthesis of ATP from ADP, and it involves oxidative reaction as well oxidative reactions as well as a phosphorylation. That's very clear that for getting ATP from ADP, phosphorylation should be there. So that is phosphorylation. So that is the entire concept. Synthesis of ATP from ADP involving oxidative reaction, that is oxidative phosphorylation. I hope that it is very crystal clear to you, that concept. Next, I am moving to another part, that is chemiosmotic hypothesis. Is very important, has asked so many times for the university examination, for 2 mark questions and also for 4 mark questions. So don't skip this one. Okay, and it's very simple. Try to understand. And this hypothesis is proposed by, that should be one of the point you have to write for this question's answer. Proposed by British biochemist. What's his name? Peter, Peter Mitchell, in 1961. And for that finding, he was awarded Nobel Prize in 1978. So next, we all know that, as we have learned about mitochondria this much, now we know that it has two membrane, outer membrane and inner membrane, and between these two membrane there present the space. What's its name? Inner membrane space. Which is that space? This space. Okay, and this is the matrix. And in the last class, I have told you that whatever we are eating, and as a result of its metabolism, certain byproducts are forming, and those byproducts are uh, holding or carrying energy rich electrons. So, which are those energy rich electron containing compounds formed out of the metabolism of foodstuff that we are eating? They are NADH and FADH2. Okay, they contain the energy rich electrons. And I already taught you that in the inner mitochondrial membrane, they are present certain protein complexes, multi subunit protein complex, and through this complex, this electron is translocating, it is moving, and because of that translocation, enormous amount of energy is releasing, and the mitochondria is not wasting that energy. Using that energy, mitochondria is pumping protons from its matrix to the inner mitochondrial membrane, and by that way they build up an electrochemical proton gradient, a gradient of proton across the inner mitochondrial membrane. And that gradient is a resource of energy, and it can move down again to the matrix in the direction of concentration gradient through the motor, the main motor that is generating ATP. What's its name? ATP synthase. Clear? So because of This energy, protons are pumping from matrix to intermembrane space. By that way, protons concentration increase here. That is called the electrochemical proton gradient. As the concentration increase here, it can passively, without the help of anything, it can flow downwards in the direction of concentration gradient through the ATP synthase. And because of that movement, this ATP synthase motor, it rotates generate generate ATP from ADP because of phosphorylation. So this is the basic process, is the main underlined process happening inside the mitochondria to generate ATP. So here as we look, we can understand that because of a chemical process, some energy rich electron carrying compounds, which are those compounds Na, D, H and FADH2 is forming. So because of some chemical process. So that chemical process is linking with the transport of electron through some protein complex. So that linking, because of that linking, what ultimately results? Generation of high energy molecule like ATP. So that concept, that hypothesis is called chemiosmotic hypothesis. Look, it is the linking between chemical process that resulted in the formation of NADH and FADH2. It is linked with the transport process of electron through these protein complexes. And because of that linking, certain high energy chemical molecule, that is ATP, is forming. That concept is chemiosmotic hypothesis. It is clearly mentioned here once more. Hypothesis says that high energy chemical molecules are forming as a result of a link between chemical process and transport process. I hope it's very, very, very clear to you. So next we are going to see, we are moving to the crux of the topic, crux of our subject. And before that, we need to understand about ATP synthase. Okay. Regarding the detailed working of ATP synthase, I have prepared another video, and its link I will give in the description box. You can go and see. And in that video, in a detailed way, I explained about the ATP synthase. Here, we just only going to see about its parts, its organization, like that. 15 percentage of the membrane proteins of the mitochondria, it is accounted by ATP synthase. We're considering total amount of membrane proteins of the mitochondria, 15 percentage is ATP synthase. There are some other names for this ATP synthase, because we need to understand those names too, because on seeing that name, we shouldn't tell that I haven't learned about this particle, this structures. So understand the other names of this ATP synthase, like elementary particles and F1, F0 particle or ATPase. So these are all alternate other names of ATP synthase, synonyms of ATP synthase. So this is the appearance of our important motor, is a motor that is generating our very, very important, our energy currency, that is the ATP synthase. Okay. And it is present in the this is the inner mitochondrial membrane. Okay, so it is fixed in the inner mitochondrial membrane. And we have seen that through the inner mitochondrial membrane, so many protein complexes are present, and through that the electrons are moving, and that will result in a proton gradient, and that protons are again then moving through this ATP synthase to generate ATP from ADP. All those things I think is clear. Okay. So in that way, ATP is formed. And next we are going to see the structure and mechanism, how it is all those things we are going to see about this ATP synthase. And who found this? Who explained all the structure and mechanism of action of this enzyme complex? It is by an American scientist. His name is Paul Boyer, and also a British scientist, John Walker. They both explained the all the mechanism. It's a reaction of the ATP synthase. So, can we have a closer look of this ATP synthase? It is a multi subunit protein. Look here. We can see that so many proteins they took the form a multi subunit protein is ATP synthase. Okay, and it spans the inner mitochondrial membrane. Okay, right. Look, it has the appearance of a lollipop. Lollipop, we all know what is lollipop. Lollipop sweet. It has a stick like spot, and over that there is a small ball like sweet. So, this ATP synthase also have somewhat appearance similar to a lollipop. So, lollipop like structure. And this ATP synthase is composed of two substructures. Substructures, which are those substructures? F1 and F0. So next I'm going to show you F1, F0, and this F1 and F0 they are connected through a stalk. That stalk we can see here. Okay, and this is the F0 portion and this is the F1. This much portion is the F0 and this much portion is the F1 portion. Okay, the transmembrane part is the F0 and that transmembrane part consists of how many subunits? 10 to 12 subunits are there. 10 to 12 and they arranged in a circular way form a channel having a central passage and through that passage all the protons can move out. Okay. Then a channel is there for proton translocation. Then F1, this part, F1 unit and that stock. This they are composed of five different kind of proteins. Which are the different types of five different types of proteins? They are alpha, beta, gamma, delta, and epsilon. And where all these proteins we can find? Look, this much area forms the F1 part. This is the enzymatic part of the ATP synthase. And look here, we can see so many subunits. This part alternatively composed of alpha and beta in three copies each. Three copies of alpha and three copies of beta. They present alternative to one another around this stalk portion. So sometimes this is alpha, then this one will be beta, this one alpha, then beta, and there in the back there will be one alpha, then here beta. So in this way, three copies of beta and one, two, and one in the back of the stock, three copies of alpha. So that is what three copies each of alpha and beta subunits. And this delta, gamma, and epsilon they form the stock. This portion and this portion, the stock is consists of this delta, epsilon, and gamma. So that's all about the organization of ATP synthesis. I think it's clear. And so this ATP synthesis is the site of synthesis of ATP. And otherwise, this enzyme is called the mitochondrial ATPase. Why? Because it is present in the mitochondria. So that is why it's called a mitochondrial ATPase. And one more thing, we learned that it is the main motor that is synthesizing ATP from ADP. So in the same way, this motor can hydrolyze ATP and release ADP. By that way, can release energy. And using this energy, the mitochondria can pump protons from the matrix to the intermembrane space also. So that is dual mode of action. Forward reaction and backward reaction. It can create ATP and also it can hydrolyze ATP. So that is why this ATP synthase are also known as reversible coupling devices, because which reaction it is catalyzing, it can carry on that process in the reverse direction also. So that's why ATP synthase is called reversible coupling device. Okay, I hope it's clear. Next, we are going to the very important, it's very simple, but we need to listen the whole topic very keenly, very concentratively. So that's the only thing. And we are going to start. First, I am going again, begin with the basic thing, basic matters. So we know that this is a structure, symbol, schematic structure of mitochondria, outer membrane, inner membrane. This is matrix, and in the inner membrane present so many protein complexes. Here. Protein complexes, and these two things are the high energy electron carrying compounds, from where it is formed because of the metabolism of foodstuffs that we have it. Uh, so that's it. And look to this protein complexes. Before moving to that, we need to understand some terms. What is oxidation? What is reduction? I think is clear. This very simple concept. I think it's known to you. I'm not going for that. We need to understand about the redox potential and redox couple. What do you mean by redox couple? Redox couple. Redox couple means in an oxidation reduction reaction, there will be one element. I'm just writing like this. Uh, just maybe different elements. One is undergoing oxidation, and the other one is undergoing reduction. So they together we can call as a redox couple. The pair that is undergoing reduction and oxidation, that is redox couple. And the capability of that element or ion, whatever it be, its ability to reduce the other one, that is called redox potential. Redox potential, simple, because it is the potentiality of whatever metal we are referring, its potential to reduce the other one, that is redox potential. So these are the two concepts that we need to understand. So look, I told you that some protein complexes are there, and they are arranged in the order of in the decreasing order of their redox potential. That means this one how high is the redox potential, this one comparatively less than that of this one, and this one might be the one that have very less redox potential. So decreasing order of redox potential, these protein complexes are arranged. Okay, so let's start. We know that these molecules are the banks of the high energy electrons. From this, the electrons are passing through this protein complexes, and after passing all these protein complexes, it is accepted by the oxygen. That is why it is very urgent that we need to breathe. We need to breathe oxygen to complete all this reaction to generate ATP. Anyhow, leave that. So after passing through these protein complexes, it is accepted by oxygen. We know that because of this transport, high energy amount of energy is releasing, and using that energy, a proton gradient is developing across the inner mitochondrial membrane, and the protons that steepened that accumulated in this space, intermitochondrial space, it is passing through this ATP synthase, and because of that movement. It rotates and results in the generation of ATP from ADP because of phosphorylation. So this is the basic thing. So we know the means skeleton of this process, electron transport chain. Then we are going to sink to its deep, sorry, sink to its depth. Mm. So these are the complexes that is present in the inner mitochondrial membrane, and this is complex 1, and this is complex 2, this is complex 3, and this is complex 4. And all these complexes have separate name. For simplicity, I will always mention you like complex 1, complex 2, like that. And once I will means mention you about the name of each complexes. You have to note at that time. Okay, we know that this space is the inner membrane space, and this space is the matrix. Okay, and this first complex, what is its name? The name of that complex is called NADH. Dehydrogenase complex. Nice name. NADH. Look that name, because it is taking electron from NADH. So that is why this complex is called NADH dehydrogenase complex. First complex, complex number 1. Okay. So from NADH, it takes 2 electrons. And I already told you that all these proteins are certain protein complex, consists of so many proteins. They arranged in an organized manner to form each single complex. And this FMN is flavin mononucleotide. Is present inside this complex, and these 2 electrons are passing to the FMN center. And after reaching FMN center, these 2 electrons are moving to certain iron sulfur clusters. Some different iron sulfur clusters are present. So we can see that 2 electrons are moving from FMN to the one iron sulfur cluster. From here moving to next one, and from this cluster it is moving to another iron sulfur cluster. What is the peculiarity of these clusters? Each one can undergoes reduction, oxidation reaction. Whenever the electrons are transferred from here to here, it undergoes reduction and it undergoes oxidation. And from here, whenever the 2 electrons move to here, it undergoes reduction and this undergoes oxidation. So in this way, these electrons are moving through all these centers inside this complex, and these 2 electrons then accepted by another protein that present here. Its name is ubiquinone. Ubiquinone. Okay. This 2 electrons, as it gain from here, it takes up 2 protons also from the matrix side. Okay, you have to note that how many protons it is taking up? 2 protons. So after gaining 2 electrons and 2 protons, it becomes the final reduced ubiquinone. QH2. And this QH2 is moving to before that, I need to mention, it's worth to mention that uh, while this process for protons also translocating from matrix to the inner membrane space. Why this happen or how it happens? Because as the electrons moves from these centers, from one center to next one, energy is releasing, and that using that energy this proton is transporting. because the ultimate result that we want to develop a proton gradient across the inner mitochondrial membrane. So that is the final aim. So that is happening as these electrons are moving through all these centers that present inside each complex. Okay. So I think there's no doubt. Two electrons is taken up from NADH, it moves to FMN and iron sulfur clusters and finally accepted by the quinone, oxidized quinone, and it becomes a reduced ubiquinone. And four protons are transporting. That is the process that is happening in the complex 1. Okay, clear? Then we are moving to complex 2. Complex before that, told you that ubiquinone is forming here, and that ubiquinone move to this area. This area means the space between the different protein complexes, and this space we can call it as ubiquinone pool. Okay, okay, leave that. Here we can see the complex 2. Complex 2, what is its name? Complex 2, it is called succinate dehydrogenase complex. Succinate dehydrogenase complex, complex 2. And this is one enzyme also, means we can see in the TCA cycle, um, in the conversion of succinate to fumarate. There's a reaction, there's a step in the TCA cycle, formation of this conversion of succinate to fumarate. That step is catalyzed by this enzyme. So during that step, this FADH2 is forming. Clear? During that succinate, during the process of conversion of succinate to fumarate, there forms the FADH2. Okay, this FADH2 carry high energy electrons. And from the FADH2, that electrons are moving to iron sulfur clusters, iron sulfur centers inside this complex 2, and that electrons also finally accepted by oxidized quinone to form a reduced ubiquinone like here. So by that way, from here also, uh, one molecule of reduced ubiquinone is forming. So here one molecule of ubiquinone, and from here, from the complex 2 also one molecule of ubiquinone is forming. Okay, up to here I think it's clear. Then we are going to see about the complex 3. What is the name of the complex 3? Complex 3. It is known as ubiquinone cytochrome oxidoreductase. So that is the name of this complex, third complex name. Why we draw? Why we means keep that position of complex 3 in between complex 1 and 2? Because these two ubiquinone that is formed from complex 1 and complex 2, they need to proceed through the complex 3. That is why for convenience it is placed, it is considered in between complex 1 and complex 2 against that successive order. Okay, let's see what is happening inside. A slight means a little complicated process. Anyway, I expresses everything in a very simplified manner. You can understand this very clearly. Look what is happening inside this third complex. Before that, once more, I am going to tell you that while considering complex 1, how many protons are transported to intermembrane space? 4 protons. here transported. And from the matrix, two protons are taken up to form one molecule of ubiquinone. Okay. And here also, for forming one molecule of ubiquinone, two protons are taken up. But there is no transport. There is no transport of protons across the intermembrane space while the electrons move to the complex 2. Why? Because the energy that is formed here is not sufficient to export protons from matrix to the intermembrane space. That's why here there is no means transport. Here only it's possible to transport 4 protons. Okay, leave that. We are going to talk about the complex 3. This is the complex 3. And here we have two ubiquinones, reduced ubiquinone, and each one contain 2 electrons and 2 protons. 2 electrons and 2 protons. 2 electrons, we know that it is possessed from NADH, and these electrons from FADH2, and these protons taken up from matrix. These protons are taken up from the matrix. And these protons from both of these ubiquinone, they are passed to the intermembrane space. And what left here? 2 electrons in both these quinones. We are taking the case of 1 electron each at a time. So 1 electron from this reduced ubiquinone is moving to a cytochrome protein that present inside this complex 3. I told you that each complex is a multi-subunit protein. So, inside this complex 3 present a cytochrome, and to that cytochrome this electron is moving. Then what is cytochrome? Cytochromes are certain heme containing protein. Heme group containing protein, water soluble protein. It can undergo oxidation reduction reaction. So that is the peculiarity. Just understand that. Anyhow, the electrons from the one reduced ubiquinone pass to the cytochrome B. And from the cytochrome B, this electron is accepted by an oxidized quinone. Oxidized quinone. Does it receive one electron? It becomes semiquinone. Semiquinone. Okay. So it got this quinone got one electron. Okay. And likewise, one electron from this reduced ubiquinone also come to this cytochrome B and pass to the semiquinone, and after obtaining 2 electrons it becomes ubiquinone. Reduced ubiquinone, and for completing its formation need to pick up 2 protons from the matrix. So that's what shown here. So by that way an oxidized quinone become a reduced ubiquinone. Okay. And this reduced one move to the pool, ubiquinone pool that present in the inner mitochondrial membrane. Okay. So, regarding the story of one electron in each of the ubiquinone is over. Then what left? One more electron. So, what is happening to these 2 electrons? Inside the complex 3, there present one more cytochrome. Its name is cytochrome C1. This one B. Okay. And this balance electron, it is moving to the cytochrome C1. And from the C1, it moves to another cytochrome. It is a freely moving cytochrome. It is called cytochrome C. Cytochrome C. So, after receiving that electron, it becomes reduced. So, that's why it is blinking. It is reduced. It is energy packed. So here also one electron left. That two pass in this way. First it reaches cytochrome C1. From the cytochrome C1, it is accepted by another cytochrome C. And by that way, how many reduced cytochrome C is forming here? 2. Okay, clear? So because of one Q cycle, we can call it as a one Q cycle. One Q cycle from the two ubiquinone. How many reduced cytochrome C are forming? Two reduced cytochrome C are forming. From one Q cycle, two reduced cytochrome C are forming. So that is one Q cycle. And that's all about the process reactions that is happening inside the complex 3. Mm, and, sorry. And we can see that here. Two cytochrome reduced cytochromes are formed because of one Q cycle. What is the fate of these two cytochrome reduced cytochrome? It have to move to complex 4, that is the last complex. And what is the name of that complex 4? It is called cytochrome oxidase. Cytochrome oxidase. So not the name of that complex, it is cytochrome oxidase. Next, we need to learn about this complex. Here, we can see that arrived reduced cytochrome C carrying one electron each. And inside this complex, there present 3 copper ions. And they are organized in 2 centers. In one center, 2 copper ions are present. So that only I am going to tell you first. Leave that. These electrons from each of the reduced cytochrome C, it is moving to the first copper center that contains 2 copper ions. It is reaching here, and from this center, it is moving to some heme group. 2 heme groups are present, A and A3. So first these 2 electrons are moving to the first heme center, that is A, and we can see those two electrons from these two cytochrome C have reached here. And as these two cytochrome C lose electrons, it becomes again oxidase. That's clear, that's simple. And from the heme A center, these electrons, one of the electron move to the second heme center, that is A3, and one electron is left in this heme. This left electron is moving to the second copper center. I told you that 3 copper ions are present. They are arranged in 2 center. One center contain 2 copper ions, and the another center contain the third copper ion, that is CuB. And this electron, the left electron, it moved to the copper B center. And by that way, these two centers possess 1 electron each. And this time, they can bind 1 molecule of oxygen. 1 molecule of oxygen, as they both have 2 electrons, 1 electron each at each of these centers. Yes, this oxygen molecule is held in this way. This bridge is called peroxide bridge. This bridge is called peroxide bridge. One molecule is held in the form of a peroxide bridge. And as these two oxygen atoms receive 1 electron each from these two centers, it can pick up 1 proton each also from the matrix. So that is up to here. That's all about the story of two cytochrome because of one Q cycle. Okay. Next, one more Q cycle is happening, and because of that, two more reduced cytochrome C is reaching here, each carrying electrons. Both these electrons are moving to the first copper center, and from that center, they both are moving to the first Heim center. And from this Heim center, one electron is moving one to the A3, and the another one moving to the copper center, that is CUB. And another more electron reached here, this oxygen atom again can pick one more hydrogen from the matrix. Then look what has formed here, one molecule of water, H2O. H2O. So by that way, two molecules of H2O is forming. Because of all these process, this electrons movement through each of the protein complex, finally what is forming here, two molecules of water. So that is the detail of this process. And here four molecule of protons also translocating across the inner mitochondrial membrane towards the inner membrane space. So that's what here enormous amount of energy is available, and using that these protons are transported across the inner membrane towards the inner mitochondrial space. So that is all about the process that is happening inside complex 4. To here we have seen. Then we are moving to our final motor. We know that by all these way, enormous amount of protons have reached in the intermembrane space, and a concentration proton gradient had built up across the inner mitochondrial membrane, and it can easily pass through the ATP synthase in the direction of concentration gradient, because we know that here the concentration of proton will be high, and here its concentration will be less. So that is what next. These protons are moving to the ATP synthase, and because of that movement, it powers this motor. It rotates, and because of that rotation, what is forming here from ADP? What will form? ATP will form and release from the ATP synthase motor. So that is the process. I hope it's very clear. And because of one complete oxidation of one molecule of NADH, it can form three molecules of ATP, and one complete oxidation of FADH2. One molecule of FADH2 can form two molecules of ATP. That is the generalized concept, generalized understanding. And next I am giving you an overview regarding the extent of proton translocation, proton taken up from the matrix. First is about the complex 1. In the case of complex 1, 6 protons are taken up from the matrix. And in this 6 protons, 4 are directly, we know that 4 protons are transported towards the inner membrane space using the energy released out of the electron transport. And what about the two protons? That two protons are used up inside this complex itself to form one molecule of ubiquinone. So that all about the 6 protons taken up from the matrix in the case of complex 1. Then regarding the complex 2. In the case of complex 2, I already told you that the electron transport that is happening inside the complex 2 is not it is not having sufficient power to pump protons towards the intermembrane space. So here there is no taken up of proton, there is no transport of protons to the intermembrane space in the case of complex 2. Then regarding the complex 3, in the case of complex 3, from the matrix, two protons are taken up. 2 protons are taken up, and those 2 protons are taken up to form one molecule of reduced ubiquinone. And we know that because of the reaction that happens in the complex 3 from that 2 ubiquinone, 2 protons are moving to the intermembrane space. So here 4 protons, 2 plus 2, 4 protons have reached the intermembrane space, but from the matrix only 2 protons are taken up. And regarding the complex 4, totally 8 protons are taken up from the matrix. And of this, 4 protons are directly translocated to the intermembrane space, and 4 protons taken up for the complete oxidation of one molecule of oxygen to form 2 molecules of water. So that's all about the overview. Totally, with regard to this complex 1, 6 protons are replaced, means taken up from the matrix. Regarding the complex 3, 2 protons are taken up. Regarding the complex 4, 8 protons are taken up from the matrix. So that's all about this electron transport chain. I think it's very clear. And also once more, I am reminding you that all of you need to go to our channel and watch the working of ATP synthase. Its video, its link I will give in the description box.
I'm an icon, man. Ain't my girl about a 10. I should fuck her in a Benz.